Sangvi. Now I would like to move to our next talk, which is RSD invited talk by Professor Deepak Kunzru. Professor Deepak Kunzru, who is also our alumnus and retired professor of our department, he is currently Dean at Graduate School of Research and Distinguished Professor at Ahmedabad University. During his tenure at IIT Kanpur, he held Chevron Chair Professorship and served as HOD, Dean Research and Development. His research, uh, he received his BTech from IIT Kanpur and PhD from University of Pittsburgh. His research spans reaction engineering, microstructured reactors, and CO2 utilization. He is a fellow of Indian National Academy of Engineering and Indian National Academy of Sciences, Allahabad. Uh, he has published over 110 articles and conferred the Institute Fellowship in 2022 by IIT Kanpur. Now I would like to request Professor Kunzru for his talk.
Good morning, everyone. So, well, I thank the department and Krishna for all the arrangements, and it's great to be back here. I first entered IIT Kanpur at the young age of 16 years, way back in 1963, together with Santosh. And after serving for 40 years, I retired in 2016. So anyway, it's great to be back. It feels like home. So I've chosen a topic, general topic on advances in chemical engineering. So many of the things which I'm going to present, I'm not an expert, but some of the things I've worked on, but many of the things are whatever I've read. Some of you might have also read these things. So anyway, let's see what we have. So first of all, let's look at some of the historical breakthroughs in chemical engineering. I don't know, the most important product at one time used to be sulfuric acid. The GDP of a country was related to the sulfuric acid production. And I think the first plant, sulfuric acid, was the lead contact. It was in the late 1700s, I think, early 1800s. And so these are the two main products at that time. Then Haber-Bosch process, everybody must have heard of this for the ammonia manufacture. I think they tested maybe several thousand combinations before they came up with the iron catalyst, which is still being used with slight changes. And then we had during the Second World War in the 1940s, we had a lot of advancements in petroleum refining because of the importance of the gas and gasoline. And in fact, catalytic cracking was the first process, and most of you would know what is catalytic cracking, so I won't go into that. But this was the first process which used, or rather I would say the other way around. Fluidized bed reactors were developed because of catalytic cracking. This was the first process which used catalytic cracking was the first process which used fluidized bed reactors. And this was in the 1940s. Before that, it was being done in fixed bed. And the problem with catalytic cracking is that the coke forms very fast. So you have to have continuous regeneration. So in fixed beds, they used to alternate, but with fluidized beds, they could make it continuous. So it was the process was made continuous. Then another major achievement of chemical engineering was in the synthetic polymers. And again, you have to be well prepared for some of, because I don't know whether, again, historically, Teflon and I think polyethylene also were discovered by accident. So they were trying some other experiment, and then they found that at least for Teflon, it was not dissolving any solvent. And then they came up with this. This environmental catalysis, in the 70s, there was a big problem of smog in the Los Angeles area. And that was the start, and that is why the catalytic converters were developed for converting the hydrocarbons to CO2 and H2, etc. And this SCR stands for selective catalytic reduction, which is basically to convert the nitrogen oxides to nitrogen. So these are some of the important breakthroughs which happened in chemical engineering. Then let's look at some of the advances. Now, the topics which I've chosen are there are other things also which are sort of important advances, but some of these things, because of my interest, I've just mentioned here. So carbon capture and utilization already Jitin has talked about a lot, but there are technologies to, well, which I'll just mention, to convert these to fuels, chemicals, and building materials. Some of these are being used right now also. For example, CO2 is being used in fire extinguishers, it is used being for enhanced oil recovery and so on. But there are other technologies which are being tried and developed. Then this is some area where again microreactors are being tried, and I'll talk a bit about them because I've worked for a few years on microreactors for various reactions, and microreactors are being tried in various ways. And this again, high gravity separation or high G is something which where Nitin Kais and Dr. D.P. Rao have worked here, and of course nanotechnology, everybody knows about it, and so there are various applications of nanotechnology. So these are some of the things I feel that are important and will be important in the years to come. So I'll briefly mention what I feel are some of the important achievements. So first of all, I think everybody knows that the CO2 concentrations are gradually increasing, and they have been increasing because of industrialization. Now, I don't know, all of you know or not, that some CO2 is required, because it has been estimated that if there was no CO2 in the atmosphere, then the temperature would be about -18 or -12 degrees centigrade. But so while CO2, what does CO2 do? It captures radiation which falls. But if there's too much CO2, then too much of it is it's not reflected back. So because of that, the temperature of the atmosphere rises, and the consequences, we know that we have global warming, rising sea levels, and so what are the ways of capturing and utilizing? So there are 3 or 4 different categories why what you can do it. One is what is post conversion. That means that after the process, you have some CO2 producing process, and this is the most commonly used one. That you have, as Ritesh also mentioned, amine process is a very common process which is being used. But so this is a mature technology which is applicable, which is being used for several decades, and all refineries have it, and other places wherever you have CO2. And of course, these are some of the limitations. Pre-conversion is basically that you remove the, so generally you have a process, for example, supposing you have gasification. So you have gasification will produce CO2, H2. So you want to remove the CO2 before you process it further. So you are sort of removing it before the process, and so this is what is pre-conversion. And then we have oxy-fuel conversion, where basically you are using oxygen instead of air. So it is a higher concentration of CO2 is produced, so the capture is easier later on. But the problem is that you require oxygen. So there the cost increase. This direct air capture is a more recent one, that is supposing if you can capture the CO2 directly from the atmosphere. And for that you require, because as you know, the concentrations of CO2 are very, very small in ppm levels, so you require very efficient adsorbents. And some of these adsorbents which have been developed, like what are called MOF, the metal organic framework, they're very high surface area. And these are being used, and they are being doped with amines, etc. And they are trying to sort of, though there have been some laboratory studies, of course, right now it is still in the laboratory stage. But if this could be something which can be demonstrated at the pilot plant level, then of course it would be a much safer, easier operation. Then what are the methods of separating CO2? Well, physical absorption is there, and this again are standard processes. For example, we have the rectisol process, which uses methanol. There is a propylene carbonate, I think that's called the floral processes. These ionic liquids, I suppose these are relatively recent ones, but ionic liquids are basically salt, but in the liquid state. And they have been, these are supposedly green solvents, and sort of environment friendly. They are being used for various applications. And there are sort of, if you look at it, literally millions of combinations of ionic liquid. And and so these are being tried. In fact, ionic liquids are, are solvent for various gases and fluids. And in fact, Chevron recently, not recently, maybe 10, 15 years back, developed a process, alternate process for alkylation, which is a very important process in petroleum refining, which is not that important in India, but very important in West and wherever the gasoline consumption is high. And there, they are using ionic liquids for the alkylation process as a solvent. It's a liquid-liquid reaction, and but ionic liquids is are being used. So they have a very low vapor pressure, so they are very environment friendly. Then these are deep, and then there are these are again a more recent class of solvents, the deep eutectic solvents, and they are in fact, some people say they are very similar to ionic liquid, but that is not the case. But again, they have I mean, in brief, what is a deep eutectic solvent? That means you have two compounds, two solids, and you mix them together in the right proportion, and you form a liquid which has a much lower boiling point than the melting point than either of the two compounds. So very common DES, or DES is a short form of deep eutectic solvent, and a very common solvent is very common DES is choline chloride and urea. You mix them together, you form a liquid, and which can be used for various applications. We have used it for CO2 reaction of CO2 with epoxide to form to form carbonate. And this, of course, chemical absorption. This is a standard method of reacting CO2 absorbing. Absorption of zeolite is a standard. Again, new MOFs are new sorbents are becoming. This MOF is the metal organic framework, and these are very high surface area materials. And again, there are several different combinations available. And depending on the metal, you have a metal, you have an organic linkage. And depends on that, how much you can absorb. And different types of, one of the problems in the absorption method is how to dissolve. So you have pressure swing adsorption, PSA, which is a standard process. This is, then you could have temperature swing adsorption, because for desorption you need a higher temperature. And VSA is vacuum swing adsorption. So these are all methods of desorption, and then the membrane separation processes which are based on. So these are the methods which are available, most of the methods. So what are the what are the methods which are being tried? Now, there are thermochemical methods which are being tried, and I'll mention some of them. This RWGS is what is this reverse water gas shift reaction, which I just found out that Gotham is doing some work, or other Gotham students are doing some work on that. And so hydrogenation, methanation, but as Jiten also mentioned, that all of these processes require hydrogen. Most of them, not all. And So we have other processes also, photocatalytic, electrochemical, photoelectrochemical. But what are the challenges? The challenge is that CO2 is a very stable compound. Is a very stable compound, and you require large amount of energy to break that bond, to convert it into something useful. And many of these reactions which have been mentioned here, which I'll just show on the next slide also, require hydrogen. And right now, how is hydrogen produced? By steam reforming of natural gas, which produces a lot of CO2. So you are not solving the problem. So because if you want to solve this problem, you have to get hydrogen by renewable energy. So these are some of the thermochemical ways in which CO2 can be utilized, and many of these things are being tried, many are known. So this is the reverse water gas shift reaction which is being tried. This CO2. So water gas shift reaction is a standard reaction. But reverse water gas shift reaction, so far it's not an industrial reaction. Then you can make methane out of CO2 by methanation reaction and so on and so forth. This DME, also dimethyl ether, there is a lot of talk about dimethyl ether being a substitute for LPG. It is also could be a substitute for diesel. And then instead of steam reforming, people are trying to have dry reforming. It has also has some problem which I'll mention in the next slide. So these are some of the limitations of the thermochemical route. If you look at the reaction, it is the first reaction. It is a endothermic reaction. So you require high temperatures if you want to have high conversion or high equilibrium conversion. The problem is catalyst sintering. The surface area or the metal area of the catalyst reduces. Generally, the catalyst for this reaction is an iron-based catalyst or copper-based catalyst. And other combinations, iron-copper combinations have been tried, but this is a problem which is being faced. One option is that, as you can see in this reaction, if you want to increase the forward rate, if somehow you could remove the water. So you could remove the water during reaction, and two ways have been tried. One is that if you have a permeable membrane which allows the water to pass through, and that is what is shown as, I don't know whether you can see it properly or not, that water permeable membrane. Or you could have a absorbent which has the water, so you have a catalyst which can absorb the water. So that is the second method, or for in situ absorption, where you absorb the water and then you dissolve it. So it's a cyclic process. Then methanation. So in this case, what I was saying that in the water gas shift reaction, which is a standard reaction, you have so whenever when you have this steam reforming of natural gas to form CO and hydrogen to form synthesis gas, you have a step of water gas shift. But there you have two high temperature and a low temperature shift. And why is that? Because high temperature is used because you can have a higher rate of reaction. But you cannot have a high because it's the water gas shift reaction is a exothermic reaction, so the equilibrium conversion is low at high temperature. So because of that, to increase the equilibrium conversion, you go to a low temperature. So you have high temperature and low temperature. But in this case, you need just a high temperature. Then the methanol, some of the disadvantages are that you require more effective heat removal. What has been tried, again these are some of the things which have been tried, is somehow if you can remove methanol, you can condense out the methanol. There have been reports where methanol can be condensed out so that your equilibrium conversion increases. But these are not industrial processes as of now. Dimethyl ether formation is something which Yale at one time was interested in. It is being touted as a substitute for LPG. It can be also used in diesel engine. Its cetane number is in fact higher than diesel. The problem is that dimethyl ether can be formed. So methanol is a standard product. Dimethyl ether can be formed by the dehydration of methanol. So it can be formed either in the, so you need two active sites, two type of active sites. One is for the methanol formation, the other is for the dehydration. So either you can have it in two separate reactors, or you can have the same catalyst with two functionalities. So the problem right now is that the yield from the CO2 is much, the yield of, if you use CO2, the yield of DME is very low. So these are some of the things which are being tried for increasing the dimethyl ether. This is again dry reforming is something which has been tried in Gautam Dev's lab, which is the problem here is that coke formation is high. So that is a major problem in dry reforming. This is what is called as dry reforming. So these are some of the problems of the thermochemical route. Then people have tried photocatalytic conversion, where these are some of the steps which are shown here that so this is the formation of the holes and the electron, and these are the reactions, so which are schematically shown here. So this is the biggest advantage of this process, that it uses sunlight as a clean energy, but there are various limitations. One is that you can have this hole and electrons can combine back to that reduces the selectivity, reduces the efficiency. This is the most commonly used material, TiO2, for this reaction. But the problem is that TiO2 can only work under UV light. So, and the recombination is very rapid. So people are trying, one thing which people are trying is that can we use some things which use the visible light also, so you can have a better efficiency. And people have used Syria as one compound which has been used. So that is one problem. Then people are using nickel, tin, copper nanomaterials, nano-sized particles to increase the efficiency. So these are some of the problems. Other problem here is that how do you make it continuous? Continuous reactors, especially in photocatalytic, you require some studies on that. Then we have the electrochemical route also, which has been tried. This process, the high temperature reduction, is reasonably well researched, and it may approach commercialization. And here the CO2 is reduced at the cathode, and so basically the electrolyte is I think zirconia, and the catalysts which are used are transition metal catalysts or perovskites which are being used. So this is something hopefully will see the light of day. Then we look at the process intensification, where a lot of work has gone on. So this is microreactors have found application in various areas, and there are several advantages of microreactors. One is that because the surface to volume ratio is very high, there the rates of heat and mass transfer are very high, basically because of the surface area. And so if you are using a microreactor, the scaling up is just numbering up. Whereas if you use an ordinary reactor, you have different size reactors. So there the correlations become different, and so you need a pilot plant in between. Supposing you have done some experiments in a laboratory scale, you cannot go from a laboratory scale to a commercial scale directly. So generally in reactors there's a pilot plant in between where your catalyst is tested out. But here in this case, the size is the same, so if you have done it in one size, you just have to number it up. So scale up is very easy, and it has found a lot of applications in pharmaceutical manufacture because of the small scale in pharmaceuticals. So this is, I'm shown some various types of microreactors. These are the channel type, these are the barrel. This is the monoliths which are being very extensively used in cars. I don't know how many of you know that whenever you are sitting or driving a car, you are sitting on a chemical reactor. And it's the most widely used chemical reactor in millions, that most widely used reactor. This is something more recent where they are using 3D printing to make such structures, open cell structures. And these are found applications. These are standard ceramic monoliths which have been used, which we have also used in our studies here. This is a metal monolith which are also commercially used. So this shows the advantage of using microreactors. So if you look at the heat transfer and mass transfer and compare with the other type of reactors or the type of equipment, you can see that both heat and mass transfer are very high for microstructure reactors. And that is the reason why most of the time they are being used. But there are other advantages also, and this slide lists some of the advantages. For example, if you are using a solid catalyst, and you all of you are chemical engineers, you must have talked about effectiveness factors. Generally, the effectiveness factors in a reaction, in a industrial reaction, because of the size, is less than unity. So in the case of microreactors, because there is only a thin film of catalyst, so the effectiveness factors are nearly unity. Plus, because of the temperature, more uniform temperature in a microreactor as compared to a bigger reactor, you could have a higher selectivity. And I've already talked about this one. This is you can have a better process control because of the uniform temperature. And since small amount of material is being used, especially for high pressure operation, you can have much safer operation. In fact, some of the things I think in the later slide. So this is shows some of the applications. I should mention that right now there are very limited applications of microreactors, but hopefully things will be better. I mean, more applications will be used on a commercial scale, because right now a lot of work is going on in the laboratory scale. So you have this, for example, this shows the catalytic converter. So this is your tailpipe or silencer in the car. And if you open it up, you'll find that there's a monolith here. And if you look at this monolith, so this size, this channel size is 1 millimeter. So this is a large size. And this is so these monoliths, the ceramic monoliths and the metal monoliths don't have any surface area, any internal area. And those who are doing catalysts know that the supports require some surface area. So this is the surface area, high surface area material which is coated here. So this is the white one is the actual coat, is the catalyst. So this is one industrial application, and the other one is the selective catalytic reduction of NOx in power plants. So this is also used. So these are some of the successful applications. This I have just shown you. This is Velocis is a UK company, and this is a operating plant of a Fischer-Tropsch synthesis. Now, Fischer-Tropsch synthesis is a potentially very important reaction. I don't know how much you know about Fischer-Tropsch synthesis, but India is trying to commercialize coal gasification. What is coal gasification? And coal gasification is what? You just take the coal and react it with steam, and you get COH2, which you want, and CO2 other things. Now, why is it important? Because once you have COH2, using this Fischer-Tropsch synthesis, you can make all the way from C1 chemicals to C20. So you have methane, you have LPG, you have gasoline, you have diesel, you have kerosene, waxes, etc. In fact, South Africa and China are the only two countries which are using FT synthesis commercially, because both don't have any oil. And this, once you have, but they have coal. So if you can utilize coal to get the synthesis gas and then use FT synthesis, then you are in business. So India is trying to utilize its coal because India has a lot of coal. The problem with Indian coal is that it has a lot of ash. So that is the problem. So the reactors have to take that into account. So coal gasification is being tested at various places, and in fact right now there are two pilot plants operating. One is by BHEL somewhere in Bihar, I think. I don't remember or Jharkhand. Other is at Thermax, which was a collaboration between IIT Delhi and I think Thermax. And if you, I don't know, when we used to go to the old DST office, there used to be a model there of that plant, that coal gasification plant. But this this technology won the Kirkpatrick Award, is given by AICHE every year for the best technology. So 2011 this got the award, and as it explains that it is just 1/10 the size of a commercial plant for the same size. So India is, as I said, India is trying to use its coal, and once that coal can be, the coal gasification plant is, coal gasification technology is ready, then this uh, reaction will become very important, and especially for some of you who will be in the professional area. So this will hopefully in the next 5, 10, 15 years will be a commercial technology for India. Then these are some of the potential applications which I've listed here, both non-catalytic and catalytic. In fact, these have been tried in some of these on the lab scale. For example, nitration of nitrobenzene, generally it is an industrial process which is conducted at I think 80 degrees centigrade, and it takes about 2 hours. Using a microreactor in the lab, the time was reduced to 10 minutes and the temperature was reduced to 65. Similarly, for oxidation of alcohol to ketones and aldehydes, the temperature, this is conducted minus 50 degrees centigrade to avoid the side reaction. And because of that, you require a lot of cooling. But because of the microreactors, the temperature can be increased to about minus 20 to 20 degrees centigrade, which is a big help. This is a big thing right now because most of the pharmaceutical manufacture is in batch scale, and we are trying to use it continuously, and microreactors are being used here because they are on a small scale, and that is where they are well suited for pharmaceutical manufacture. So many companies are trying to make their batch scale continuous using microreactors. And these are some of the catalytic reactions. In fact, we have tried steam reforming of ethanol here at IIT Kanpur when we were when one of our PhD students. Steam reforming of methanol has been done in a microreactor. The problem is that methanol is anyway obtained from synthesis gas, so it doesn't help. But steam reforming ethanol has more problems, so that is still not a commercial process. But for portable applications like fuel cells, etc., this technology in microreactors is important. So these are some of the technologies which have been tried. For example, steam reforming of methane. Because it is done at very high temperatures. It is this temperature. I don't know. Those of you who have taken technology courses must have learned that this is what temperatures of the order of 700 degrees centigrade, 800 degrees centigrade. At those temperatures, the effectiveness factor of this reaction is very low. Is about of the order of 0.01 or something, 0.1 or 0.01. If you use a microreactor with a thin coating, then the effectiveness factors can go up. So that is the advantage of using a microreactor for steam reforming of methane. Again, multi-phase catalytic reactions. For fast reactions, it is the mass transfer which is controlling. And for mass transfer in certain operating regimes or certain hydrodynamic regimes, the mass transfer coefficient in microreactors is very high in the gas liquid flow. And again, we have tried hydrogenation of alpha methyl styrene to cumene. Here, one of my PhD students was working, and we found that this was better than a trickle bed reactor, which is the standard one. So these are some of the potential applications of microreactors. then there's the potential application of high G. High G is what? You just have a rotating packed bed, and you have a packing here, and you have a gas flow and a liquid flow, and basically you are increasing the mass transfer coefficient. And as I mentioned that this technology was developed here. In fact, HPCL has taken that technology. They claim that they sort of worked on it and filed another patent, so there was a big problem. But anyway, this has been patented by us, by IIT Kanpur also, and so this is significant achievement, significant size reduction of contacting equipment is possible using these rotating packed beds. So this has been tried. So these are some of the areas which I've taken this slide from somewhere, and you can see that it has been used for separation, it has been used for nano materials, it has been used for making ultra small metal organic frameworks, and so on and so forth. So this has, again, one of the problems here is that you have to have a continuously rotating equipment. So chances of failure are there. So that is one of the limitations here of this technology. But there are, especially in China, they have used it for pharmaceutical industry. And there are plants operating in China. So this has been used at various places, used in refineries for separating hydrocarbons, and there's a significant reduction in the height of the column. I mean, tall columns can be made into small size equipment, and so there's a factor of 5 somewhere also I was reading. So reduce column height and energy consumption compared to traditional distillation. So this is a very sort of technology which has a future, and as I said that the HPCL is operating a pilot plant. I don't know what is the status of that. Maybe is running, nah? Is running, and I think Hyderabad. Where is that? So it's running, and they were doing, I think, desulfurization. So let's see what happens. Then it is being used in gas, various places, CO2 capture. So you can see that there's some numbers here that absorption is increased 2 to 5 times. And then these are some of the applications of Hig in reactions. It can increase the transacidification. Basically, you are increasing the mass transfer. So wherever you have mass transfer limitations, it can help. So these are all places where you have mass transfer limitations, and because of that, your separation and purification in the downstream processes are reduced. Then they have been also produced and used in nanomaterials. How much time do I have? So this is high G application, nanoparticle synthesis. So these MOFs are a big thing these days. These are the metallo-organic framework, and the reported surface areas are as high as 10,000 meters square. Where typically a catalyst may have surface areas of 200 meters square per gram. Active carbon, which is supposed to have a high surface area, has about 1000 meters or 800 meters square per gram. So these have very high surface areas, and very lot of different combinations are possible. And so they are being tried in various as they are being tried as catalysts, they are being tried as catalyst support, they are being tried as adsorbents. So they have lot of potential applications of these metallo-organic frameworks. So this is listed somewhere here. So nanotechnology, everybody has heard about nanotechnology. It is being used in various places for energy production, catalysis, drug delivery, and so on. So again, this shows you some of the applications of nanomaterials and energy conservation, energy transmission, and so on. So solar energy, quantum dots are small transistors, and perovskite-based nanoparticles are giving you more efficient solar panels. Then in battery technology, nanostructured materials reduce the degradation of batteries. Fuel cells, they increase the reaction rate. Energy storage, you graphene, CNTs, these are carbon nanotubes, are used in supercapacitors. So all of them are sort of nanomaterials are being used in all these applications. So these are some more examples of nanocatalysts, and basically the high surface area to volume ratio increases the activity. So you have these PM fuel cells which uses platinum, and again nanoparticles give better performance. Biodiesel production, nanocatalysts give a better performance, and so on and so forth. So this is the standard method. These are in the conventional methods of drug delivery. So nanocatalyst has been used for drug delivery, and these are some of the problems: poor absorption, poor bioavailability of the traditional medicines. So because of this, the nanomaterials are being used for targeted drug delivery, which is, so these are the materials which are being used for targeted delivery, and these are again nanoparticles are being used for targeted delivery, and these are the different types of nanoparticles which are being used. So this is just how the nanoparticles are used. So Siddharth Panda is not here, but I suppose his students know better. So this is the kind of biosensor standard application, standard design. You have a biochemical conversion where you have various either one of these things, and then you have some sort of a transduced signal, electronic display. So again, these are nanotechnology based materials. Then there's a lot of advances in biotechnology, biorefinery. And biorefinery is any type of biomass. So there are, if you take any biomass, there are three things. One is the cellulose, one is hemicellulose, the other is lignin. So cellulose, of course, is being used for various places, but hemicellulose, so people are trying now to use the hemicellulose as well as the lignin and the various ways of using it, and you can get various products. And there are operating refineries, in fact. So you can, these are the feedstocks which can be used, consumer residues, agricultural residues, by, so different types of residues. And what are the different ways of harnessing the energy? These are again standard reaction. Gasification, this is again biomass gasification. You can react it with steam to give you gaseous fuels, then of course you have to clean it out. Then pyrolysis is heating in the absence of air, and again these are standard processes. In fact, my first MTech student way back in the 70s, the first project which I gave, MTech project, was pyrolysis of bovine waste, that's gobar. So that was the first project I still remember. So, but still you can, any carbon containing compound you can pyrolyze. So pyrolysis of biomass is a big thing. Then this is a process which has already been commercialized. This thermal hydrolysis, it is a two-stage process. You have a high pressure boiling and a decompression. And I think the next slide has it. So this is a flow sheet of an operating refinery which uses this thermal hydrolysis. And this is a refinery in, I think, Denmark. So this first process using thermal hydrolysis was in Norway in 1996. And since then there are, what I was reading, there are 30 plants which are using this thermal hydrolysis process. So this shows the refinery, operating refinery, various things which you can produce from a refinery. So you can see that different types of waste are being added here from agriculture, from industry and so on, and you get different types of products. So this is nowadays various places. In fact, there are, the other day there was some visitor who was writing there's a waste aggregator. So agricultural waste from farms, they collect at various farms and they sell it. So they are, this is, I mean, this is in India. They're waste aggregators. So they'll take the rice husk, I mean, from field. This is not from industry. Then you have different aspects of various ways where advances have taken place in bioengineering, nanomedicine. So these are all places where chemical engineering has had an effect. Then these are the computational methods which have, which have been there for some time. So these are the different scales. You have micro scale operation all the way to macro scale. The macro scale is something which which chemical engineers have been doing for a lot of time. Micro scale also, but there's a new thing which is the multi-scale modeling. Right from, for example, I know that because that is of my interest in for a steam cracker, they first looked at the chemical reaction. There are hundreds of, in fact, literally thousands of reactions going on in a cracker. They use those micro scale modeling to get the detailed kinetics or detailed model, kinetic model, and then use CFD, etc., to design the reactor. And this has been done in Belgium. So this is a multi-scale modeling, all the way from micro scale to macro scale is a big thing. And because you need different types of numerical methods for the micro scale, different methods for macro scale. So it's not a straightforward thing. Although micro scale alone is okay, macro scale alone is okay. But multi-scale is something which is coming up. So there have been lot of applications of computational chemistry Many of them are, many of the faculty here and students, I'm sure, are working on these. This is molecular dynamic simulation. Professor James is working on these things. And so this is something which will continue. There are methods to quantum mechanical methods are being used to understand chemical reactions. And this is a very important thing, that these things help you in development of catalyst. Because up till now, catalyst development was more or less a trial and error method. It still is to some extent, but with the help of some of these theories, you can limit or restrict the kind of dopants and kind of catalysts or active metals you want to try. So a combination of theory with experiment is I think, the forward way. So some of the other applications of computational chemistry is you can study the environmental impact of pollutants, what are the mitigation strategies. So this is again density functional theory. DFT stands for density functional theory, and this is again a lot of work is being done on this DFT calculation. So these have applications in various areas, and so they have been used for batteries, they have been used for semiconductors, and so on. Then, of course, this is a buzzword these days, AI and ML. I don't know much about it, I don't know. But everybody is talking about AI. And I heard there's a course being offered of AI in chemical engineering by Sanjeev. So they have been applied in various places. ML and AI, although they are used interchangeably, what I understand is ML is a part of AI, is a subset of AI. ML is basically data driven. Earlier you used to have neural networks, etc. It's, I think, an extension of that. You need lot of data, and then you train the model, you use part of data to train it, and then it is hopefully does a good job of predicting. So this has been applied in catalyst development and so on and so forth. But what it is, I think I have, yeah. So it has been, these are some of the places where the machine learning has been used, and this is the limitation, that there is no universal data set for catalytic activity. If you want to use it, then you require a lot of data. And for some reactions, it has been used, and some of the reactions have been mentioned here. There's a steam reforming of methane, dry reforming. So ML has been used to correlate. But what I understand that sometimes you need some sort of a descriptor for this, and sometimes it can lead to spurious correlation. So this is something which you need to be careful. But every whatever I have read mentions that you need more data, especially more sort of selected, proper data for if you want to use it for catalyst development. Then this ML has been aided with DFT calculation, because DFT calculation can be used to predict some properties, and properties are required by machine learning. So this is something that DFT calculation have been combined with machine learning, and to reduce the sort of to select suitable candidates for catalyst development, because otherwise you have a much wider choice. So this is just to limit your experimental effort, and this is something. This is from this reference. Again, This is AI and combination with, has been used to predict the formation of new hybrids. Because I mentioned that you have several, without exaggeration, millions of combinations of MOF, and you can use AI ML to predict some of the experimental conditions for the formation, whether a MOF will form or not. And this, of course, you can integrate this with molecular modeling for the design of new adsorbents, and this has also been used. Again, this is something you need to train the thing, because X-ray diffraction is what? You need to read the data. So machine learning has been used for rapid interpretation of some of this characterization data. This is X-ray diffraction, electron microscopy, this is X-ray fine structure analysis, and other data. So ML has, so this is something which is being used, or it has been used. Then this is something which you have a, you want to predict what is the property of a molecule, and it has been done for some cases. You take a molecule, you make it into a molecular graph, and then you have the AI processing and you get the molecular property. So this part is not that difficult. But the holy grail is the other way around. That supposing you want the molecular property, what molecule that you should use? Now that is something which is a dream of chemists and engineers. That again, it could be a molecule, it could be a polymer or whatever. Supposing you want some molecular properties, what should be the starting point? If that problem can be solved, then of course there's a lot of achievement. But there's been some success, but there's a long way to go for this reverse problem. This problem is more manageable. This reverse problem requires a lot of work still. So I think that was my last slide. So basically, I have not talked about sustainability at all. That is a big thing these days also. But these are some of the challenges which are still remaining, because these are some of these things I've already mentioned. That for utilization, if you want to utilize carbon dioxide, most of the materials, most of the methods require hydrogen and energy. So these have to come for renewable sources. Otherwise, you won't be able to do much. And so this is a limitation. For microreactors, one of the problems, I did not go into the details, but catalyst loading is a problem, because you can't load too much of catalyst. So if you compare volume by volume, the amount of catalyst loaded in a reactor, in a standard reactor, would be much more compared to a microreactor. But then there are other advantages. And you need a better understanding of hydrodynamics, especially for multi-phase reactions. And this again, I've mentioned that machine learning is data driven and there's lack of suitable data. So that was my last slide.